Oh, hello and welcome back. Here we are again, 2, 3, 4. I'm still disabled-ish. I've swapped the trusty Honda Shadow VT750 V-twin for a Zimmer frame with handy accoutrements bag. I've got my handy reacher that bust the other day, cheap fucking Chinese shit. Lots of drugs, paracetamol, ibuprofen. Oh, I've got an interesting valve in here, which we'll have a look at in a minute. I've got my knife, I've got my nicotine spray, I've got nicotine patches, I've got some nice drugs in here if I get bored. Short tech, hurrah! Oxycodone, hydrochloride, hooray! Anywho, let's try and get this bugger working, shall we? What have we got here? In the last video I covered the output stage pretty much. As you see, it's all cobbled together with jumpers and things. I want to go through that in a minute to make sure that's all cushy. Standing on one leg. Snazzy different socks on today with the Go Faster yellow stripes. I've just had a look at the front end because I couldn't remember what the bleeding hell I'd done, and here is my conclusions. We've got some information missing. 6 and 2 PEV 12B 87. So I've gone for something a little bit different here ish, in that my front end is a paralleled 6N2P EV, which is a Russian ECC83. But it's different, like a lot of Russian valves. They're not B9A, the B9E, like the ECC88, meaning that the pin 9 hasn't got a 12 volt. Basically, they haven't got a 12 volt heater. They're just 6.3. Pin 9 being a screen up the middle of the two, separating the two anodes. So I've got the two anodes strapped together with 247. Actually, that's wrong. I fucked up there. That's going down there. Sorry about that. Hope you can see that. So 247k resistors, 247k anode resistors, 1k cathode resistors. Now then. Hold on, I'm still wrong, aren't we? That's where it should be, like that, right? So, what happens if you strap a triode in parallel? You get twice the current. If we get twice the current, we get twice the current going across these anode resistors. So you don't need to use this bigger anode resistor. So, a pretty bog standard setup for a ECC83 type valve is 100k anode resistors to give you quite a lot of gain and all the rest of it. But because we've got twice the current going through these and they're in parallel, so what we got there, half of 47, it's about 43k, right? No, it isn't, you peanut, it's 23k. But we've got twice the current, so we should have the same voltage developed, AC voltage developed going across these. I'm not quite sure why I chose 47k. I should have used maybe just one resistor, one anode resistor with the two watts it's strapped. I don't know what the bleeding hell I was thinking. I was trying to get a load of gain out of it. I think what I was trying to do, this is a long time back before the accident, was trying to get a really high gain front end, and I just sort of threw it together as usual. Same at the bottom end, the cathode, all strapped together, two 1k resistors in parallel, so that means that's 500 ohms, because we've got twice the current. We're still going to develop about the same sort of cathode voltage. For an ECC83 type, you want to be sitting at about minus 1.5 volts. So we don't run into grid current. and that is just basically coming out there into our trusty old 12B87 long tail pair phase splitter. I haven't put a resistor in here, have I? Got a grid leak here, so we've got to set our control grid to about 0 volts. Without that, that'd just be floating. So we do need that 1 meg. Basically, when I'm throwing together a stage, 1 meg, 10N coupling capacitor, and you're sorted. That sets your that basically forms a high pass filter at about 15 Hz. So everything over 15 Hz or something like that, don't quote me on that, gets passed straight through. Okay, what we're saying, yes, we've got a whole long tail pair driven from our constant current source. I've got this underneath there, that's the magic ingredient, because when I had it before I was testing it and it touched this high voltage underneath there, so that's just providing a bit of insulation. We've got a usual bit of decoupling. We've got 100 microfarad there, decoupling the long tail pair from the HT, and I don't know what's down there, something like 150 microfarads. Basically just to stomp on the ripple. All that, as you see, is going, we've got a green, what do you call it, jump lead, yellow jump lead. So one green's going into the output stage, jump lead's going into the output stage, and the other one's going into the right hand side. Although this is the Heath Robinson affair, let me sit down because my bleeding leg's falling off. My left leg's falling off. Hold on. Hook a duck. Oh, sorry. Everything hurts. Anyway, that's better. God, I put the scope on a while back and it's still bleeding cold in here. We're at the beginning of November 2021. High winds. It's been persistently raining for the last few days. High winds, all that malarkey. Typical British winter weather. Well, winterish weather. Right, where was we? It's all Heath Robinson, but we've got protection, don't worry. We've got a big mains fuse here. Can't remember, it's something like 3 amp. Slow blow. We've got another fuse coming out of our bridge rectifier there. The rectifier diodes are avalanche types in series to increase the peak inverse voltage rating. So I think there's something like 600 volts, 800 volts, so that increases that to 1600-ish volts peak inverse voltage. We've got a fuse, AC, you know, because it's AC, oh no, it's DC, isn't it, coming off here. That goes into two big 820, no, it goes into one 820 microfarad capacitor, into the choke, into another 820 mic, and at the moment all that is feeding is the screen grids. And here, hiding at the back, is that simple circuit that I think I showed you in the last video. That's just regulating the screen grids to 300 volts. Right, we've got our big power supply going into the centre tap of the output transformer, which applies the output stage. Here we go then. Nice sine wave output at 4.2 volts RMS. That's about 3% harmonic distortion. If we swing around here, you can see the harmonic content. We're at 300 volts screen grid supply, 300 volts anode supply. As you can see, we've got second, third, fourth, fifth, etc. harmonic distortion. Quite a bit of it. Whoops, knocking things out. We're running at minus 29 in a bit. Bias on the output stage. and on one valve we've got 43 milliamps. What do you call it? 43 milliamps current. I know, cathode current. Okie dokie. So let's up the anode voltage to. Sorry, I'm going to point you at something, aren't I? It's a bit hard standing on one leg. 350. I'll point you to the harmonic, to the FFT. You see that's gone down. All those harmonics down here have gone down a bit. We've now got 4.6. Let's have a look what we've got distortion. And that's gone down to 1.2. I don't know what's going off there. Okay, we've had to change to the Tektronix 585 instead of the 545. The display's not as good because I can't alter the triggering preset. Yeah, look, I've upset the bugger now, look. Fuck. Yeah, the triggering's not as good. When you know, we had this problem before on one of the videos. I had a problem with this 545 and I adjusted the preset and that sorted it, but the preset is stuck on this one. Anyway, where was it? So let's crank the anode voltage up. 4.6 volts, 4.6 volts RMS, 1.2 volts, 1.2% harmonic distortion. I'm cranking up the HT. B+. As you can see, our second harmonic is going down. Our third is going up, and we're at 400 and a bit volts HT. So the second's gone down, third is now dominating. We've now gone up to 4.9 volts RMS, and we're getting a lot less though harmonic content. Right, let's just crank that all the way up, watching the harmonic content. All the way to 500 volts. 1.4, 1.2. Alright. Right, and that's it. I'm at 500 volts. And as you can see, the EHT, the THD has gone down. As you can see here, that's gone down. What if we want the second to predominate? Right, I'm going to try and hold this still while standing on one foot, one leg, etc. So let's see if we can get that second harmonic up. See, that's starting to poke up a bit now, look. And we're at 400 volts. Sorry. See, that's edging above now, look. Second is going above the third. And we now have 0.7 THD. And we're just a little bit above, below 400 volts. Right, let's crank the bugger up and see how much we can get out of the thing. Not really after, this isn't why I'm trying to test this, but 5, 6, 7, 8, 10, 21, and as you can see, our total harmonic content has gone out the fucking yin-yang, pardon my French. I don't really want to do this with a test setup. Could we get lower? Let's reduce the output to 2 volts. What's the lowest THD? Well, this is just for fits and giggles, yeah? Let's crank the HT up. Sorry, HT, I'm getting my terminology mixed up. See if we can get that below 0.0. There we go, look. That's with a HT of 420 odd volts. Crank it up some more. I'm turning the B+ HT up. Right, now what did we have at 8? Right, 0.08 at, oh sorry mate, the camera work's not very good because I'm standing on one leg, 2.3 volts. Let's see if we can just adjust the volume to get that less. I'm just mucking about here. No. Alright, right, that's just gone below what it can detect now. 0. Yeah. Crank that up some more. Raising the HT. That's going up now. Where did we have it before? 1. We wanted it 2, didn't we? Right, we've got 0.09 THD, right? And as you can see, our harmonic content is very little. Now I'm going to lower the HT B+. Harmonic content is going down. Sorry, not very good bloody camera work, I do apologise. Still at 0.09. Reducing it quite a bit more. Right, and now our THD has gone up and we're sitting at 0. No, we're not, we're sitting about 350 volts. Now watch what happens when I reduce that. No, I'm just going to do this quickly. I'm at 300 volts now. So our screen grid, basically it's running as a triode, right? Because our screen grid supply and our HT are effectively at the same voltage. Now I'm just going to briefly reduce the HT under the screen grid, and I don't want to do that very long because they're going to be then acting as the main path for electron flow. See how that goes up. I don't want to do that for long because I haven't got big grid stoppers on there. So I hope that demonstrates what effect HT has and all that sort of malarkey. The other thing that we can do, right, let's bung that at, where did we have it quite low? Right, here we go, look, where was the, let's crank that up a bit. And which bloody, there's that many knobs and whatnot. Right, we're at 3. Right, we're at 6 volts-ish RMS output. Let's try and get, I'm cranking the HT up, trying to get that second up. No, you see it's going down. Our output is increasing, but our second harmonic, so let's reduce our HT, and as you can see now our second harmonic is predominating. Only a little bit. Let's go on above the third. Right, we're at 300 volts there. Now then, what I'm going to do now, I'm going to unbalance the output stage. Right, I'm going to unbalance one side of the output stage. At the moment it's at -29. I'm reducing that to -28. -26. -24. The third is going up, as you can see. And that's really starting to put a big struggle on my power supply. I'm going to turn that back up. I don't know if you heard that. but that was the power supply going into current limiting. So that's just a quick look at what I'm trying to sort of look at with this prototype setup. Let me sit down. So yeah, that's what I'm trying to achieve with this with this prototype setup. At some point I need to work out a way to get more than 500 volts. As per a data sheet, 600 volts. Let's have a look at the data sheet. Now then, the one thing I haven't discussed here is our, what do you call it, our primary impedance of the output transformer. You can see we've got a range from 5,000 to 10,000 ohms, basically 5k to 10k. Now, our output transformer is 3.4k. Because we're running 4 valves or 2 valves in parallel, then we basically halve what we need, or for the sake of argument here, let's double that. So let's call that 6.8. Yeah, let's call that 7k. Right? Let's call that 7k output impedance, which is sort of about here. Yeah? Because that's what it affects. That's what 1 pair of valves is seeing, basically. And sorry, yes, that's what 1 pair of valves is seeing, and these figures are for 2 valves or 1 pair of valves in push-pull, right? So let's see, we're sort of about here. 500 volts plate voltage, anode voltage, screen grid voltage 300, minus 27. We're at minus 29, which is a little bit more than we want to really be running in class A. That's one thing we didn't look at, biasing the output stage to see what effect that had on it. Unfortunately, the potentiometer to change that is right down there amongst all these sort of lethal wires. It's a bit hard to get at. I'm going to have to try and reconfigure that so we can adjust that more safely. And it needs 2 hands to do it as well. So here we go. Let's just read this column here. 500 volts HT, 300 volts screen grid, minus 27 volts on the grids. This is just a peak audio frequency grid to grid voltage 54 volts. So that would be, I think this is peak. So we'd want a lot less than that RMS. Plate current, no signal, 100. Now then, we were only getting about 43 volts, 43 milliamps, so our conditions are off there. Screen current, just ignore that, output impedance. Now let's just read down, 2.6% total harmonic distortion. Our lowest figure, alright, our memory went, where was we? Our lowest distortion figure is 2.2% total harmonic distortion for a little bit higher, what do you call it, HTB plus of 600 volts. But we also increase our, what do you call it, grid bias to minus 29, which is about where it was set before. So what does all this tell us? What does all this testing and mucking about and looking at the datasheet tell us? It tells us a few things. It tells us that although changing the HT and other parameters does increase total harmonic distortion to some degree, it doesn't really change it that much dramatically. How much it changes the actual sound of the amplifier, that's another thing. Looking at the computer display and figures on the audio analyzer there doesn't really tell you a lot. Really, the best way to gauge whether the amplifier sounds good or not is with your ears, and that's the best way. But what it does tell us is that and this is the beauty of valve amplifiers, is that it doesn't really matter what voltages are, what your primary impedance is, within reason, and all the rest of it. Because valves, you know, the odd few 10s, 20, 50 volts doesn't really matter. You saw what total harmonic distortion we was getting with a lash up like this. I mean, we was getting less than 0.09% total harmonic distortion. With all this just lashed together, thrown together, no real design as such. I mean, I just, you know, think of a value for a anode resistor and just chuck the bugger in. So you see what can be achieved with not a lot, really, not a lot of thought. I'm a follower of on DIY audio, and they go into a lot of things like, oh, this has got to be right, that's got to be right, this has got to be right. And some of the lads on there, they'll say to design the power supply, they'll go and there's a thing you can get on Duncan amps which is called B+and. It's a power supply design tool. They'll go into there, design the power supply, draw load lines and all the rest of it. Yes, if you want to really design an amplifier properly and really learn the subject properly, you can go into all that. I mean, I do read the Radio Designer's Handbook, which is the Bible of valve or tube amplifier design. I do read that, and I do read other PDFs online and things, but in the end I just chuck the bugger together and we end up with an amplifier that sounds good, you know, to my ears at least anyway. So apart from, I mean, I don't really need to spend much time on this. I didn't really need to build this at all. I could have just gone straight, you know, gone and built the amplifier straight away, to be honest. But what I really wanted to do was find out what sort of winding I need on this big transformer here for a HT. You know, try and find the best one. But really, I need to bother with all this. I could have just, you know, chucked like a few windings of about 100 volts and then just chose one that sort of sits about right. One thing I probably will do is just muck about with the grid bias a little bit more. See whether we can get the, you know, the second harmonic up. But you can do that just as easily by not matching all the output valves. You see, really, if you want really low total harmonic distortion, all of these valves should be matched. I haven't matched these, I've just chucked these in. That should give us more second harmonics, because this is a push-pull stage. It has a thing called a common mode rejection ratio. The more matched and balanced that is, say by using these two pots here and using matched valves, the less total harmonic distortion you get. But if we want really low total harmonic distortion, I'd just go and buy a bloody transistor amp which has got a total harmonic distortion of 0.0000 whatever. But that's not what I'm after here. I'm after an amp that sounds good. I mean, the lads who record an album, they muck about with it, sticking distortion on. I mean, there's a story of a, I don't know if it was the Beatles or the Stones, somebody like that. They went into this studio, you know, 1960s. All the engineers there have all got brown or white coats on, like freaking lab technicians. And one of them, let's say it was John Lennon or whatever, just pushed the faders up so that the VU meters were pegged out going into distortion, and the engineers were going, oh no, freaking out and everything. But that's the sound they wanted. So therefore we can sort of expand from that. That's not quite the right word I'm after. We could, you know, we can basically, if we design an amplifier and build an amplifier, we can add a bit of coloration onto that if we want. It's not a crime. If we want bloody tone controls there and there, we want a bit more bass, that's not a crime. that's okay. Our ears change as we get older anyway. I mean, I can't hear much over 12, 14 kilohertz. So I like a bit of treble on my amplifier. So I mean, what am I doing there? I'm altering the sound, I'm boosting the treble. It's not pure. It's not, you know, exactly how it left the recording studio. I mean, that's a load of crap as well. Because every pressing of a vinyl LP is different. You look at the Beatles LPs, every pressing was done differently. They boosted this frequency, boosted this a little bit more, depending on, to a great extent, what sort of equipment it was played on. So they sort of boosted certain frequencies for the record players at the time, which were old crappy dansets and things like that. So basically what I'm trying to do, I'm trying to make a case for mucking about with the sound of an amplifier. Instead of going for a straight wire with gain, let's throw in a few harmonics of our own by design and make this thing sound pleasing to our ears. Not wrong with that. Anyway, I've waffled on long enough. I'll get up off my soapbox, get this edited, uploaded, and it's something for you to watch. Anywho, can't think of anything more to say. Think that's it. Hopefully you should be getting a few more videos for a while, as I'm sort of housebound. Bugger all else to do that play with amplifiers all day. It's the life, innit? And anywho, take care of yourselves. Hope you're keeping alright out there. And ta-da for now. Or is it that way? Ta-da.